Okay, so this day we have here Arthur Gretton. He will tell us about very interesting technique based on kernels, which is a competing technique, complement to neural networks. So please.
Okay, can everybody hear me? So we're doing an experiment. I'm going to use this until people tell me they can't hear me, and then I'll switch. But so don't be shy to tell me if I'm not loud enough. So I'm Arthur. So thank you for inviting me. So today I'm going to talk about kernel methods, and for the next 2 days. So thank you for waking up early for this. I should also say at the start, I really like to get questions. So please, if anything is not clear, or if you have some nice ideas, stop me at any time, and I'm going to be happy to answer any questions that you have. This will be especially essential in the next lecture. So the next lecture has slides that I never gave before, so they're not going to be clear at all, and that means that you have to ask me to clarify things. Okay, so I'm going to talk about kernel methods. And before I sort of go into technical details, I want to give a little bit of context, a few problems that I'm going to be addressing in the next 3 days. So the simplest of these contexts is comparing samples. So I've got here 2 sets of samples. I've got a set of samples of dogs and a set of samples of fish. And just from these samples, I want to know whether P and Q are the same or different, okay? So 2 sets of samples, dogs and fish. And from these samples, I want to know if P and Q are different. So this is the one problem I'll address. Here is a specific instantiation of this problem. Let's say that I'm a very clever scientist and I made a mechanism for generating images of handwritten digits, okay? So on the left are real handwritten digits. On the right, there are digits generated by GAN in this instance. And I want to know whether the real digits in the, are distinguishable from the fake digits. Okay, I want to know if my generative model is so good I can't tell real from fake. Now, the people who wrote this paper, they went to Amazon Mechanical Turk and they said, humans are distinguishing these at chance level. That means that my real handwritten digits and my fake handwritten digits are equally good. There's a problem with this. The problem with this is that, humans can miss things that machines can find. So for example, imagine that my computer digits were doing too many ones relative to the proportion of ones in real digits. That's something a human wouldn't detect. Or let's say that computers were more inclined to do ones which are sort of leaning the wrong way, leaning to the left rather than the right, in a way that's quite unnatural for a human. If you're a human, you still think these are realistic digits. But a machine will tell you, well, actually, you're drawing digits in a way that's a little bit unnatural for a human. So I want to be able to make this distinction, and I'm going to find a way to detect these kinds of differences that are maybe too subtle for a human to see between samples. All right. Now, if I have a way to tell apart sets of real and fake objects, I could also use this to train generative models. So let's say I have a generative model of bedrooms in this instance, and I want to make my real bedrooms look like my fake bedrooms. I have a criterion for comparing real and fake samples. I would then minimize that criterion so that my set of real bedrooms and my set of fake bedrooms look as similar as possible. This is something else that we're going to do. So in the lectures tomorrow, I'm going to talk about using the measure of distance between real and fake sets of objects to train generative adversarial networks. All right. So I've talked about differences between sets of objects, and this is, tomorrow I'm going to be talking about this and nothing else, okay? But there's other problems I can also address. So one is imagine that I have a model and I have a set of samples. I want to know how well my model fits my set of samples. So in this picture here, the little red dots, these are crimes committed in the city of Chicago. And so you can sort of see a distribution of these red dots. These are where crimes are committed. Then I fit a very bad model to this. It's a mixture model with just 2 Gaussians. You can see it's a bad fit, okay? And what I might want to know is, how bad is this fit? And where is it fitting badly, okay? So rather than comparing one sample and another sample, like a sample of real digits to a sample of fake digits, in this instance, I'm comparing a sample to a model. So I've got a sample, my set of points, which are my crimes in Chicago, and then I've got a model, a mixture of 2 Gaussians. I want to know how far away the sample is from my model. Okay, here is the final setting that I'm going to talk about. This setting is the setting of testing independence. Okay, so what I have here is, in a sense, like two complementary views of the same object. So X, in this instance, is an image of an animal, and Y is a caption. All right? So the caption is describing, in a sense, the animal. But the caption isn't describing the animal in an obvious way. So like an obvious description would be, this is a brown animal, it has 4 legs, it has a tail, it has a nose, okay? This is not what the caption says. The caption says something which is sort of, descriptive of the animal, related to the animal, but it's not a literal description. So it's a large animal who has a houndy odor and wants to follow his nose, all right? So if I'm an expert on dogs, I could take the captions and I would know that that caption referred to that dog. But I'm not an expert on dogs. What I want to know is whether the images in the captions are dependent, even when I am not able to regress from one to the other. So let's say I'm not an expert on dogs, I don't know how to regress from caption to image or from image to caption. Nonetheless, I want to know whether these pictures and these captions are dependent on each other. So whether the caption is related to the image. So it turns out, the problem of regressing from caption to image, that's a hard problem. The problem of testing dependence is an easier problem. That might surprise you. So in the very last lecture on Friday, I'm going to talk about how to solve that problem. All right. So these are sort of motivating examples. These are the kinds of problems that we're going to be able to solve at the end of this series of talks. Today, I'm going to give you a little bit of foundational material on kernels so that for the, when I talk tomorrow and the next day, you're able to understand, the mathematical principles underlying all of the things that we're going to discuss. All right, so this is what's going to happen today. Today I'm going to talk about what is a reproducing kernel Hilbert space. So these are the mathematical tools we're going to use in the next 2 days. Reproducing kernel Hilbert space, it's 4 words, and I'm going to break that down into little subsections. So first of all, what is a Hilbert space? Because this is not a functional analysis course, that will just be a couple of slides, and I'm going to wave my hands and ignore all the complexities. Then I'm going to talk about what a kernel is, which is actually something very easy. Like, a kernel is not a mysterious object, and I'll describe it. And then finally, the reproducing property. Okay, so reproducing kernel Hilbert space. The reproducing property is where I'll spend the most time because it's, in a sense, like one of the most interesting things. Yeah, the main thing that you should get out of this lecture, though, is this 4th point here, using kernels to enforce smoothness. So kernels are a way to construct functions which are smooth in a way that I'm going to describe in very, very, I think, granular detail. And this is, I think, the most important property that you're going to get from today's lecture. Okay? I'll also talk perhaps a little bit about some classical results, but I'm not going to dwell on those. And given the time limits, probably I won't talk too much about that. All right, so your incentive to wake up early tomorrow, tomorrow what we're going to do is we're going to talk about a measure of difference between sets of objects. So this is the problem that I started my lecture with. It's called the maximum mean discrepancy for reasons that I'll talk about tomorrow. I'm going to talk about how to do a statistical test with this metric, so how to tell if my 2 samples are sufficiently different that you can't just explain it by chance. And then I'm going to talk about how to use this metric to train a GAN. So this is sort of like a fun part of the talk. Then in part 3, I'm going to talk about testing whether a model and my sample are different. So remember my crimes in Chicago and my terrible model, like where is my model going wrong? And I'll talk about testing dependence. Okay, so my images and my captions are my images related to my captions. All right, reproducing kernel Hilbert spaces. Okay, so there are 2, I guess, mental pictures that you should have in mind when you encounter a reproducing kernel Hilbert space. So let's start with the first. In this setting here, I have points, red and blue points, and I want to classify red from blue, but I'm only allowed to use a linear classifier. Okay? What that means is that, in a 2D setting, I'm only allowed to use a straight line. In a 3D setting, I'm only allowed to use a plane. So what you can see from this figure is that in 2 dimensions, there is no straight line which is going to separate red from blue without error. Okay? I hope you can see my mouse. If I draw the line here, then of course, you know, these red points here are going to have the wrong label, and so on. Okay, so one notion of kernels, which is actually, you know, the same sort of trick that a neural network does, is that if I use high-dimensional features of my points, then it might be possible to separate them without error. So in this case, the high-dimensional feature space is just 3 dimensions. The third dimension is just the product of the first 2 dimensions. And that lifts the blue point above the xy plane. It pushes the red points below the xy plane, and then I can use a planar classifier, in this case the xy plane, to separate red from blue. So one notion of kernels is that it's a way of taking my points, moving them into a high-dimensional feature space, such that problems that are difficult to solve in the original space are easy to solve in the high-dimensional space. This is one view of kernels. I think this is sort of the classic view of kernels, so I'm presenting it here for this reason. This is, to my mind, a more interesting way to think about kernels. What kernels do is they give you, in a sense, a class of functions which you can control smoothness, okay? So let's say now I'm doing regression, not classification. I'm trying to do a line between, you know, a line that fits these points. Now the first line that I've drawn here is too smooth. Too smooth. The second line I've drawn is like too wiggly. And then the final line is, you know, more or less correct for this set of points, okay? So I've got, you know, I'm doing a curve. My curve is going through my points, and I'm trying to make this curve go through the points with a small amount of error, okay? And so somehow, you know, I haven't told you how yet, but I'm controlling the smoothness of this line. And, you know, I've made it too smooth, I've made it not smooth enough, and then I've made it just right, using, you know, some mechanism, all right? So now my question would be, like, what is that mechanism? And another question would be, what on earth does this have to do with this picture? Because these two seem to be very different pictures, right? Like, how do these relate? So at the end of today's lecture, you will have the answer to that question, I hope. All right. So I said that I would break down reproducing kernel Hilbert space into 3 parts. First is Hilbert space. So this part I will spend almost no time on. A Hilbert space is a space with a dot product, all right? So, you know, a dot product, you can think of it if you're in just finite dimensions with vectors as just the dot product between 2 vectors, A transpose B, okay, where A and B are vectors. You know, it has a couple of properties. So if I've got, you know, a sum of 2 vectors dot producted with a third, it's the sum of the 2 dot products with scaling alpha and alpha 1 and alpha 2 in this case. So you have linearity. You also have symmetry. F dot producted with G is the same as G dot producted with F. And the dot product of F with itself is non-negative, and it's 0 only when F is 0. So these are the properties of a dot product space. All right? In particular, like the norm, the length of a vector, is just the square root of the dot product of that vector with itself. So hopefully this is sort of undergraduate math. All of you know this. A Hilbert space is a dot product space between elements with an additional property, which I'm absolutely going to ignore for the rest of the 3 days, which is that the Cauchy sequence limits are in this space. So if you know functional analysis, you'll know what that means. If you don't have to care. I'm putting that there so mathematicians don't yell at me. Okay. What is a kernel? A kernel is just a dot product between features. That is all that a kernel is. All right? So that's, in a sense, like if you have a kernels course, I could stop my course right there, and you would know what a kernel was. So let's say, you know, x and x prime, these can be any objects. So remember when I started my talk, I had pictures of dogs and fish. Or I had captions, like text, okay? Like there's all sorts of things that I could use as my x and x prime. If I can define vectors of features of these objects, then I can define a kernel. A kernel is just a dot product between features. How I come up with these features, I don't care. I could use a neural net. I could use, you know, whatever I want. I could have hand designed features. Kernel is just a dot product between them. Okay? Another interesting point is that, like, the features might not be unique. So I can define more than one set of features with the same dot product. I've given a trivial example here where I've just sort of split x into 2 bits such that the dot product between these 2 bits is the dot product of x with y. This is sort of to say that, when I'm defining a reproducing kernel Hilbert space, the kernel is unique, but the features are not. And it's sort of trivial to see why not. You can always cook up different features with the same dot product. In this case, the example that I've given here is a trivial example. There are less trivial examples as well. All right. So now you all know what a kernel is. So when constructing kernels, it's helpful to use some tricks to sort of start with simple kernels and get more complicated kernels. Okay? So one way of doing this is to take the sum. The sum of two kernels is a kernel. All right? So if I've got K1 and K2, I take their sum, then this is still a valid kernel. And this can be useful because, let's say that I have one kernel which is very good at distinguishing shapes and another kernel which is very good at distinguishing colors. I could take their sum, and that's a valid kernel, which takes into account both colors and shapes. Now, to prove that the sum of kernels is a kernel, I'm going to need a property which I haven't yet told you, so I'm not going to do that yet, but I'm going to do that later. Okay, but now, sum of kernels is a kernel. So the difference of two kernels might not be a kernel. Can anyone guess why? Yep.
Because you have a kernel matrix, right? And it's actually the ground matrix. It's a scalar product between this feature space.
Yep.
And when you take the difference, you can violate this positive definiteness.
Yep. No, that is correct. So the difference of two kernels means that your kernel matrix might not be positive definite. What this relates to is the following. Remember, the norm of f is the square root of the dot product of f with itself. A kernel is a dot product of features, right? Now, if I take a difference of two kernels, a difference of two dot products of features, and let's say I take the kernel of x with itself, so k of x and x, right? So K1, first kernel of x and x, is positive. K2, kernel of x and x, is positive. But K1 xx minus K2 xx could be negative. That means the dot product of x with itself is negative. The length of the features is negative. That's clearly wrong. And so, this is basically what has gone wrong with this option. I cannot have a vector of features of negative length. That would be nonsense, at least for the purposes of this lecture. Yep?
So in the definition of a kernel, the original set X doesn't have to be in a space, or it can be later to this set?
X is a set. Just a set, no structure, no metric, nothing. Yeah. The features are a Hilbert space. So I design features of my objects, which are a set, and these features are in a Hilbert space. But only the features need to have that structure. Any other questions so far? Okay. If anyone's hidden behind the screen and wants to ask a question, just yell, and I'll find you. Okay. Okay. Another trick one can use is products of kernels. So products of kernels are also kernels. Okay? I might have my kernels on my shapes, my kernels on my color. Product of these kernels is a kernel on shapes and colors combined. So this one I can prove for you right now. I don't need any extra properties to prove this. I can show you how this proof works. Okay? So let's say I have phi1, my first feature. My first feature only tells me shape. Okay? So I've got an indicator of a square, indicator of a triangle. My world has only two shapes. It either has a square or a triangle. If I see a square, I make a 1 in the first entry, a 0 in the second entry. If I see a triangle, 1 in the second entry, 0 in the first entry. So a feature of a square is 1, 0. The kernel, the dot product between features of a square and a triangle, is 0. Kernel between square and square is 1. I have a second feature space. This feature space is the feature space of colors. Okay? My world only has two colors, red and blue. All right? So again, my second feature space, if I see blue, I put a 1 below, I put a 0 up here. And my kernel between red and red is 1. So I've got two feature spaces, I've got two kernels, I want to combine them, and I'm going to combine them by taking the product of the kernels. So let's show that this is a valid kernel. Okay? So what is a sensible feature space for a space with both colors and shapes? Well, this is this big feature space here, which has basically indicators of all of the possibilities. So I've got 2 colors, I've got 2 shapes. So that means I've got 4 possible things that can occur. Red square, red triangle, blue square, blue triangle. All right? And you can see that this matrix, I've written it as a matrix rather than a long vector, because I want to write this matrix as an outer product. So I've got this outer product of the color features with the shape features. And this gives me the color and shape feature matrix. All right? So what is a kernel, right? My kernel is the sum over all possible pairs of colors and all possible pairs of shapes of the color shape features. Okay? So if the colors agree and the shapes agree, my kernel will be 1. If there's any disagreement, my kernel will be 0. Okay? Now, because I've written these as a matrix, I can write this as a trace of this outer product, phi1, phi2, and this second outer product, phi2, phi1. Phi2, phi1 transpose. Okay? If I do this trace of this product of outer products, I'm going to get this double sum. You can prove that to yourself. It's a very short proof. Okay? Now what do I notice? I notice that this inner phi2 transpose phi2 is actually the kernel between colors. It's a scalar. So I make that substitution. The next thing you notice is that the trace, I can cycle my elements around. So I've got phi1 transpose phi1. That's also a scalar. It's the kernel between shapes. So now I've got a product of kernels. So indeed, the product of the kernels is a valid kernel. It's the kernel which is 1 if the colors and the shapes agree. So you can see now what a product of kernels is doing. It's like an AND operation. It's saying, if the features in K1 are similar and the features in K2 are similar, then the product will be large. If either of these is dissimilar, then the product will be small. It's a valid kernel. Okay? Now, the other option that we had was like the sum of kernels. And in a sense, you can think of a sum of kernels like an OR operation. If the colors are similar or the shapes are similar, then my kernel will be large. So this is, ways of taking simple kernels, which might account for different features, and getting out another kernel, a new kernel, which is combining our different views which our different kernels provide. Okay, so sums of kernels are kernels, products of kernels are kernels. Now, if sums of kernels are kernels and products of kernels are kernels, well, I can just make a polynomial, and that's going to be a valid kernel. So here I've just taken k of x prime. I've just taken the standard dot product between x and x prime, which is a kernel, just obviously, because it's a dot product. I've added a non-negative c, non-negative because otherwise I might get some negative norms, which are a problem. I've raised this to the power m. M is a non-negative integer. This is a valid kernel. Okay? It's a valid kernel because sums of kernels are kernels and products of kernels are kernels. All right. So all of the kernels that I've discussed so far are with finite feature spaces. And in a sense, like the power of kernel methods is that I can deal with like very large feature spaces or even infinite feature spaces. So the moment that I start talking about infinitely many features, now I'm moving sort of away from neural network land into a land with, shall we say, like a little bit more ways to trip you up. Because when you've got infinitely many features, things can go wrong which don't go wrong in linear algebra, and one has to be a little bit careful. Okay? So let's think about, how we're going to be careful here. So here is some notation I'm going to use. This little L2 notation means the sum of the squared elements, okay? So let's say I have a sequence A, it might be infinitely long. The norm in this little L2 norm of this sequence is the sum of the squared elements of that sequence. Okay? So if this norm is finite, then even if I've got infinitely many elements in that sequence, the sum of the squared elements is finite. So these elements must be getting smaller and smaller and smaller, so that the sum of the squareds of these elements is finite. All right? So let's say I've got an x, a picture of a dog. I've got features of that x. These features might be infinitely many. My kernel is the dot product of these features. I might have infinitely many features. But as long as the sum of the squared features is finite, then this kernel is well defined, it's finite. So one of the things that might break when I have infinitely many features is that my kernel might be infinity, which is a very boring thing to have. As long as the sum of the squared features is finite, my kernel will not be infinity, even though I've got infinitely many features. Okay? Here's how we know that this is true. If I take the absolute value of the dot product of the features of x and x prime, this is less than or equal to the sum of the squared features of x times the sum of the squared features of x prime. So the dot product between two vectors is less than or equal to the product of the norms, the products of the length of those vectors. So as long as the vectors are finitely long, as long as their L2 sums are finite, then my kernel will not be infinity. So this is one of the things that could have tripped me up when I had infinitely many features. I just might have had an infinite kernel. But as long as the sum of the squared features is always finite, that won't be a problem for me. Okay. So, how does it look like to construct an infinite feature space kernel? So here I'm going to give you the kernel that, if you download a kernel software package, this is probably the option that it's going to be implementing. This is the exponentiated quadratic kernel. That's also called the Gaussian kernel. It's just the exponential of the norm of the difference of the inputs divided by sigma squared. This is an example, this is perhaps the most famous example of a kernel whose feature space is infinite. Okay? How do I construct that infinite feature space? Well, here in this second line, I've written an eigenvalue problem for my kernel, right? I've got this k xx prime times its eigenfunction, integral over some probability is equal to the eigenfunction times the eigenvalue. So this is just, the functional value of what you would do in linear algebra with a kernel matrix. Okay? I've got a kernel function, it's sort of like an infinite dimensional kernel matrix. I get its eigenfunctions, and I get its eigenvalues. What that means is that I can express this kernel as a sum of the eigenvalues, lambda L, times the eigenfunctions, ELX and ELX prime. Okay? Just like for linear algebra, I could express my matrix as the sum of the eigenvalues times the outer product of the eigenvectors. Same thing. Okay? Now this P here is something that's necessary. This is sort of going to weight my sum here. So this is a way that I can construct my infinite feature dictionaries for my kernel. If I use a different P here, I will get different dictionaries of features, but I'm going to get the same kernel out. So let's have a look at what my feature dictionaries look like. If I use as my P the Gaussian, this is what my feature dictionaries look like. These are actually Hermite polynomials with a decaying envelope. Don't worry about the details of that. Just have a look at the features, okay? I'm summing these features up. What you'll see is that these features, as I go up my feature dictionary, these features get more and more wiggly, okay? So basically, as I go up my feature dictionary, I get more and more complicated features. But I'm also noticing another thing. As I go up my feature dictionary, my lambdas are decaying. They're getting smaller and smaller. So I'm saying that my kernel is a sum of dot products between features, but the features that are very complicated get smaller and smaller weight. Why do they get smaller weight? Remember that the sum of the squared features has to be finite. Another way to understand that is that the sum of the features times these lambdas has to converge to this Gaussian or this exponentiated quadratic kernel. Okay? So I solve this eigenvalue problem. I get my eigenfunctions, I get my eigenvalues. I use these eigenvalues and eigenfunctions to construct my features, phi of x and phi of x prime. So this is an explicit construction of features to get a kernel. Yep? Yep.
But they're kind of sorted, or?
Yep, so these are sorted. So lambda 1 is the biggest, lambda 2 is the next biggest, lambda 3. Yep, that's right. Yep. Any other questions about that? We're going to construct another feature space later as well. Like, I'm going to do this a couple of times because it's, I think, very, very important. But as far as this goes, are there more questions about this for now? Yep. Right, so in this case, like to get this exponentiated quadratic kernel, I need infinitely many features. Some kernels, if I just had a simple feature space like x and x squared, that would be a valid kernel. That's a polynomial kernel. In a sense, like the power of kernel methods is that I can deal with infinitely many features, as long as I can compute the kernel in closed form. So here's an example where I'm able, if I'm using a neural network, I always have a finite feature dictionary by construction. In this case, I have an infinite feature dictionary. But I never need to write those features down explicitly. I only need to write down their dot product. So as long as my algorithm only uses dot products, I'm able to use and manipulate these infinite feature dictionaries. When I'm comparing probabilities, I need an infinite feature dictionary. So this is sort of in a sense, preempting my second lecture. If I have, for instance, a probability, I only compare the mean and variance. My distributions might still be different. They might be different in higher moments. So if I'm comparing probabilities, I will need an infinite feature dictionary to do that correctly. Any other questions? Okay, so this is one construction of a kernel using an infinite feature dictionary. Yeah, and as I was saying, as long as my algorithm only uses dot products, then wherever I see my dot product, I can use these infinite feature spaces because I can write the dot product in closed form. So this is, in a sense, a very useful property. I'm able to construct an algorithm using infinitely many features, even though I'm not able to write them all down. Yep. Yeah, so A, B, and C absolutely depend on sigma, but I'm not going to write those expressions down. Yep, no, this is absolutely true. So you can approximate this kernel using a smaller sum. So if you're familiar with random Fourier features, this is using that exact property, that these are actually decaying fast enough that I might be able to get away with using a finite dictionary. This is actually, there's a very large body of literature on using these tricks and on figuring out how many of the dictionary elements we need. So that's a very good point. Any other questions? Okay. So a property that we can use with kernel methods is a property called positive definiteness. So let's say I have a function. It takes in 2 arguments. And I want to know if this function is a valid kernel. Okay? So if I can write down my feature dictionary, then I can, if my kernel is a dot product between these features, I'm done. Okay? But sometimes, for instance, in this example here, it's a little bit hard to derive your feature dictionary. Okay? But I might still want to know if my function is a kernel. There's a shortcut to determining whether a function is a kernel, which is positive definiteness. If my function of 2 arguments is positive definite, then I know that it's a valid kernel. All right? What is positive definiteness? So positive definiteness is the following property. Let's say that I have n points, x, okay, x1 through xn, and I've got n scalars, a1 through an. These scalars can be positive, negative, doesn't matter. Okay? Let's say I take this double sum ai, aj, k, xi, xj. If for whatever n, number of points that I choose, for whatever x, the points that I choose in my space, and for whatever a, the scalars that I choose, this double sum is greater than or equal to 0, then my k is positive definite. Okay? Strictly positive definite means that for distinct x, this is always greater than or equal to 0 unless all of the a's are 0. So there is a nice statement, there's an if and only if statement. If my kernel is positive definite, then it's a valid reproducing kernel. If my kernel is a valid reproducing kernel, then it has to be positive definite. Okay. I'm going to prove just one of these directions. Okay. If my kernel is a dot product between features, then it's positive definite. Okay. This proof is actually really easy. It fits just on 2 lines. Okay. Here is my double sum. Sum over ai, aj, k of xi, xj. I know that my k of xi, xj is the dot product between features of xi and xj. I know my dot product is linear. That means I can take these AIs inside the H dot product because of linearity. Now, what does this look like? This double sum here looks like the sum of AI phi xi dot producted with the sum of aj phi xj, right? Which is the norm of the sum of AI phi xi squared, right? Dot product of something with itself is the norm squared. Now, the norm squared is non-negative. It's the length. It's the length of the sum of these features. So I'm done. Okay, so I know now that if my kernel is a dot product between features, then it's positive definite. Proving the other direction is probably 10 pages of very hard math, so I'm not going to do that. Okay, now a few slides ago I promised you that I would prove that the sum of two kernels is a kernel. Now that I have positive definiteness, this proof is trivial. All right? So here is my sum of two kernels, and I'm applying this positive definiteness result. All right? So I've got the double sum AI, AJ, K1 plus K2, because I've got my sum of my two kernels. Right? Now I just split this sum into two sums. Each of these sums is non-negative by positive definiteness. That means the sum is non-negative, then I'm done. Very short proof. So now I know that the sum of two kernels is a kernel. Okay. Final property, reproducing property. Okay, so this is the, in a sense, hardest part. Okay, so remember, right at the start I talked about this very simple feature space where I took my points and I mapped them into a very, very slightly higher dimensional space where I added a third coordinate, which was, the third coordinate which allowed me to separate red from blue using a linear boundary. Okay? So, here is what I just described in math. I've got my x, my little blue and my red points. I take my two features, x1 and x2, of these points. So these are my x1 and x2 coordinates. I add a third coordinate, which is the product of the first two. That's the z-axis in this plot. Okay? And this is my space of features. I can define a kernel. Kernel is just a dot product between these features. I can define this plane using entirely dot products. So all of this is quite conventional. Okay, you've seen this all before. All right, now let's say that I want to define a function of these features. Okay, so a linear function of these features is just a weighted sum of the features. In this case, I've got three features, x1, x2, and x1 times x2. So my linear function of these features is just f1, first coefficient, times x1, f2, second coefficient, times x2, f3 times the product of the first two features. All right? Now, if I write f dot, or sometimes just f without a dot, but with no argument, that refers to these coefficients. Okay? If I write f of x, it means I've taken those coefficients, I've dot producted it with the features of x, and that's a scalar. So f or f dot means a vector of coefficients. F of x means I've taken that vector, I've dot producted it with the features of x, and I get a scalar out. So that's, f is feature space dimensional, f of x is one-dimensional, always. Okay? So sometimes I'm going to leave out the dot. Like the dot is just, I'm using it just now and then to remind you that it's a vector of numbers rather than just being a scalar. Okay? So, my feature space is three-dimensional. And I'm defining a space of linear functions that are mapping from x1 and x2 via this feature space to a scalar, to f of x. All right? So, I can do that for 3 dimensions. I can also do that for infinite dimensions. So let's say that I have f1, f2, f3, f4, f5, f infinity. Okay? There's all of these f's. I've got my feature dictionaries. I've got these phi1, phi2, phi3 from the exponentiated quadratic kernel, which I introduced earlier. I can define this function here, okay? Remember that, the dot product of these features is my kernel. My f is a inner product of features of x with these coefficients, and my norm of f is the sum of the squared coefficients f. Okay? Now, my norm of f has to be finite, the sum of the squared coefficients has to be finite, so that f of x is finite. And that's exactly the same argument that we made already, right? The dot product of the coefficients f with the features is upper bounded by the norm of f times the norm of the features. So my norm of f has to be bounded for my function not to be infinity. Okay, so now I've defined a function of infinitely many features. But, you know, it's a little bit annoying because like I now have to write down infinitely many coefficients and infinitely many features, and that's a lot of work. So maybe I don't want to do that work. So how do I write a function of infinitely many features without writing down infinitely many coefficients? So let's look at this. Here is a function. It's a function of infinitely many features. I've written here coefficients f times features of x. Okay, this is my x-axis. Here is my f. I need infinitely many features to express that function. All right? But let's say that I've taken, you know, my little f's. They just happen to be a sum of m features of points at xi, right? The features of the points at xi, there's infinitely many such features. I take a weighted sum of phi of xi with weights alpha. There's m of these xi's, m of these alphas, and this gives me my f, right? My vector of features. My vector of coefficients. Okay, so I've constructed this vector using a sum of features of a few points that I've chosen. I'm allowed to do that. All right? So now I use this property that the dot product between these f's and these features x, you know, I can just write it like this, sum over alpha I features of xi, features of x, dot product in my feature space. But then remember the property of linearity, and remember that the dot product of features of xi and features of x is the kernel between xi and x. So now I just have a sum of kernels between xi and x weighted by coefficients alpha I. These might be positive, these might be negative, okay? So now I've built up my function by taking a sum of kernels. So what is the take-home message here? The take-home message here is that if I can write this f, this dictionary of features, as a sum of features of xi, a finite sum, where I've chosen my xi appropriately, then this function of infinitely many features can be expressed as a sum of kernels. So, you know, this is a supposition, right? Because I've said that, like, you know, my particular choice of f is one that I can express as a sum of finitely many features of xi. Is this always true? Well, you know, not necessarily, right? Because it turns out that the Hilbert space can also contain the limits of infinitely many sums of features of xi. But the, I guess, pleasant thing is that the solution of most learning problems with kernels can be expressed as finite sums. And so this is true for all of the problems that you care about solving. Are there questions about this before I go on either side? Right, yeah, so that's a good question. So, right, I've said, you know, somehow I know that I have this m here and that I can solve it. Now, the m that you will get in practice will depend on the problem you're trying to solve. So in classification, if you're using, let's say, a support vector machine, m will be some fraction, like 10% of the training points. If you're comparing samples from P and Q, m will be the number of points from P and Q. So, yeah. I may be able to decrease that a bit and still get a good answer, but like that's sort of the naive answer to that question. So yeah, so the choice of m will depend on the problem that you're solving. But what's pleasant is that you can prove that m will be at least finite. So I'm not going to have to, you know, deal with infinitely many m's for practical problems. Any other questions? Yep. Yep. So basically, like, if I want that I have a function of two arguments, x and x prime. Now, I would like that function of x and x prime to be a dot product between features of x and features of x prime. This property, like this is the core property. This property will only be true, well, this property is true if and only if k is positive definite. So basically, like, the moment that I'm talking about features of x and x prime, I'm talking about a positive definite function. It's the only function of two arguments which has the property of being a dot product between features. So it's basically like the set of all functions of two arguments that I care about for the next 3 days are the positive definite functions. Yep. Okay. Any other questions? Okay. So let's continue. Okay. So, here is a kind of like slightly confusing trick, which I want to alert everyone to. So remember that I said that my function is a weighted sum of kernels at xi and x, okay, with weights alpha I. Okay, this is the example I gave on the previous page. That's happening if I've chosen my coefficients to be the sum of the coefficients alpha I times features of xi. Now, this function here is a sum of m m alphas and m xi's. What if I choose m equals 1 and alpha equals 1? It's valid, it's a function. Okay? This is what my function looks like. It's just literally the kernel between x1 and x. Okay? That is a valid function. All right? So now I can write this in this notation here. So this notation here means that, here is my f dot. My f dot is a vector of coefficients, which I dot producted with my features to get a function. But my f dot here are the features of x1. And that's fine, because the feature of x1 is a vector of coefficients. It's also a function, right? It's also a valid function, because I can take these coefficients, I can dot product it with the features of x, and I get out a number. And that's a function of red x. Okay? So here, like, my k of x1 comma dot is a way of expressing the fact that this is a function indexed or parameterized by x1. It's a vector of coefficients parameterized by x1. But it's symmetric, right? So I could write it the other way around. I could say that red x is parameterizing my function, and I'm taking the dot product of this function, this vector of coefficients, with my features of x1. I can do it either way around, and it's equally valid. Okay? So the feature map is a function. The feature of x is a function as well. It's a very simple function. It's just a vector of features of x1 or x, depending on which way around I write it. Okay? So in a sense, like, I could write my feature of x1 as k of x1 dot as a function, or I could write, k of x1 dot as features of x1. So these are completely interchangeable for the purposes of my discussion. Okay? I've said a function is a vector of coefficients. Features of x1 is a vector of coefficients. Therefore, feature of x1 is a function. Okay? So I can write without ambiguity the kernel between x and y as a dot product of k of dot x and k of dot y. So features of x are also, functions parameterized by x. Features of y are also functions parameterized by y. It's just, this is purely a notational thing, which is sort of saying that I can write, k dot x equivalently with phi of x and k dot y equivalently with phi of y. Okay? So I'm going to sort of use this notation here. So this is, when people talk about the reproducing property, this is what they mean. Okay? The dot product of f with the features of x, or k dot x, is f of x. Okay? And in particular, the kernel between x and x prime is the dot product of features of x and x prime, or the dot product of k of dot x and k of dot x prime. So when people talk about the reproducing property, this is exactly what they mean. But because of the way that we've approached this, this should be actually very trivial for you, because we already know that the dot product between features of x and x prime is just the kernel. And we already know that the dot product of f and features of x is f of x by construction. So, the reproducing property is sort of presented sometimes as a very mysterious thing. I think for you guys it's not mysterious at all. It's actually like a pretty easy consequence of the way that we've constructed these spaces. Are there questions? Okay. So right at the start, I talked about functions in a reproducing kernel Hilbert space being smooth. Now, I think, now that you've sort of seen that the kernel is a dot product between features, and you can construct those features, and now that you know that functions of these features are weighted sums of the features, you can guess already a little bit why it is that functions in this reproducing kernel Hilbert space are smooth functions. But now I'm going to go into a little bit more detail about this idea. Okay? Let's just check the time. Okay, good. Okay, so here is a kernel. This is the exponentiated quadratic kernel. And remember that I've written this kernel as a sum of features of x and features of x prime, where I've constructed these features using the eigenfunctions, ex, and eigenvalues, lambda, of the kernel. Okay? Remember that these features become less and less smooth as I go up the feature dictionary, and I've ordered my lambdas such that my lambdas are getting smaller and smaller as I go up this feature list. Okay? Now, remember that I define my functions of these features as a dot product of FL, the coefficients, these are a list of coefficients, times these features, lambda L. Okay? Now, my FL in this case is a sum of m alpha I features of xi. Okay, just as I showed a couple of slides ago. This is the figure from a couple of slides ago, reminding you that this function can also be written as a sum of kernels. But this is the form that I want you to think about right now, this form up here. Okay? So you can already see why this is a smooth function. The lambdas are decaying, right? The lambdas are getting smaller and smaller as I go up with my L. My features are getting less and less smooth as I go up my L. Okay? My f's, the sum of the squared f's, has to be finite, so these f's also have to get smaller and smaller as I go up my feature dictionary. So that means that the non-smooth features are going to have, in general, very small coefficients. So that means that my function that I get out is going to be a smooth function. In particular, remember the norm of f is the sum of the squared coefficients of f. What does that mean? Well, actually, if my norm is small, if I'm forcing my norm to be small, then these f's have to decay fast, and my function is going to be very smooth. Are there questions? Yep? So yes, because the eigenvalues of a positive definite function are always non-negative. Yep. Yep. So this is another reason why positive definiteness matters. Yeah. Any other questions? Okay. So I've sort of provided this as a quick intuition for why the function is smooth. I'm going to now give a construction of a new RKHS, and I'm going to show this smoothness again in a little bit more laborious detail. Okay? So I'm going to construct an infinite feature space using a tool that I hope that many of you will be familiar with, which is Fourier series. So actually, to give me an idea, I'm going to give all of the mathematics that we need in this lecture, but could you just raise your hand if you're familiar with Fourier series so I know how many people? Excellent. Good. Then this example is going to hopefully be really, really clear. And I like this construction because it really shows why it is that the function in the RKHS is smooth. Okay? So here is the notation I'm going to use. Here is my function of x. Okay? I'm going to write it as an infinite sum of coefficients f hat, my Fourier series coefficients, and this complex exponential, which is cosine plus square root of -1 times sine of Lx. Okay? So this is a standard Fourier series representation. It's for a function on the interval from -pi to pi. Okay? And everyone keep in mind that these complex exponentials form an orthonormal basis of functions on -pi to pi. So the dot product of e to the Lx and the complex conjugate of e to the imx is 1 if L and M agree, the scalars agree, and 0 otherwise. Okay, so the complex conjugate, for those who don't know, it just means you switch the sign of this here to -1. or equivalently, you switch the sign here to -1. So the sign of the imaginary part just goes negative, or flips from positive to negative, or negative to positive. Okay, so this is my orthonormal basis. And my function I'm going to write as the sum of these cosines plus square root of -1 times sine. Okay, so let's look at a nice example. So this is one of my favorite examples. It's the top hat function. Okay, the top hat function is a sort of function which is square on the interval minus t to t and then goes to 0 from t to pi. Okay, now I can write you here the Fourier coefficients of this. It's sine of L times t, the width of my top hat, divided by L times pi. And here is my function. What do you notice about this function? Well, it's the sum, not from minus infinity to infinity, but from 0 to infinity, of 2 times these coefficients times cosine. But my sine has disappeared. So why is my sum over half my space and my sine disappeared? Well, these f's are symmetric. This sine is anti-symmetric. So all of the sines cancel. Cosine is symmetric, so all of the cosines double up, and I get 2 times f times cosine L. Okay? So this is the top hat function. And I've expressed this top hat function as a sum of these basis functions, cosine plus I sine, in this case just cosine, times the coefficients f hat L, my Fourier coefficients. I'm going to show you this now graphically. Okay? Here is my top hat function. It's 0 on an interval from minus t to t. It's 1 on an interval from minus t to t, and then 0 from t to pi. Here is the first basis function, right? I've got a 0 frequency offset, which is just a constant offset to push my cosine up a bit. And then I've got my first cosine basis function, cosine 1 times x. All right? This is, on this bottom drawing here, bottom right drawing, I've got my f hat L coefficients, my coefficients. And remember what these coefficients were? They're sine of Lt on L pi. Okay? So I've taken this coefficient, I've multiplied it by this basis function, and I'm approximating my top hat with a single cosine. Is that a good approximation? Well, no, it's not. Okay? But what if I add, well, okay, the next coefficient for this basis function is 0, as it happens. So we throw that away. What about this basis function? Well, this basis function has a little bit, a very small negative coefficient. Now I'm adding this cosine to the first cosine, and now it's starting to look a little bit more like my top hat. All right, this one gets a 0 weight again. This one gets a tiny positive weight, it's getting a bit closer, and so on and so on and so on. So the more cosines that I add, the closer my Fourier series representation gets to the function that I'm after. So you can see that I'm expressing this function as a weighted sum of features, in this case, Fourier features, cosine features. Are there questions about this? Okay. What about my kernel? Here is a kernel. My kernel is a difference in this function of a difference of the arguments. So, think of the exponentiated quadratic kernel. It's e to the norm of, x minus y, etc., etc. Okay? So if my kernel is a function of the difference of its arguments, then I can express k of x minus y as a Fourier transform of this complex exponential of x minus y, right? The argument to my function is x minus y. Okay? And then I can express this as the square root of k times features of x, and the square root of k times the complex conjugate of the features of y, where I just switch the sign of my imaginary part. This should look familiar to you, right? Here I've got some scalars with a square root times some features. Where have we seen that before? Let's go back. We've seen that before here. Okay? So this should look a little bit familiar to you, right? I've got these square roots of scalars times these features. So in this case, the eigenfunctions of my kernel are these, the Fourier basis functions. The eigenvalues of my kernel are the square roots of their Fourier coefficients. And what is my p? What is my measure here? Well, it's just a uniform measure on minus pi pi. So here is an example of a kernel that I've constructed from complex exponential features, on the space that I care about, on the space minus pi pi, which I'm dealing with. And it just so happens that these features are the Fourier features. So this is a really nice construction of a kernel from features that you will have all learned about in undergraduate math. Yep?
So I understand correctly. So every time that your kernel can be expressed as difference between x and y, then you have this connection with Fourier.
That's right. Yep. Yep. And the fact that you can express it as a connection to Fourier, this is true for translation invariant kernels. There's a theorem called Buckner's theorem, which guarantees you that this is the case. If your kernel is not translation invariant, then no. Okay? And there's lots of interesting non-translation invariant kernels. But for this case, you have this beautiful result. I really like this result because it means that I can use just Fourier arguments to construct my space. Are there more questions? Okay, so for this special case, I've constructed my kernel using a Fourier argument. Now, here is a really nice kernel. It's the Jacobi theta kernel. So it's using a slightly peculiar notation here. But what this kernel is, it's a version of the exponentiated quadratic kernel for, basically compact domains with periodic boundaries. So remember, I'm on the domain minus pi pi. I'm assuming a periodic boundary. So when I hit minus pi and keep going, I just get, pi. Okay? So think of the axis sort of wrapped in a little circle. This is what the Gaussian looks like. So it's a sort of Gaussian that repeats periodically every, interval 2 pi. And the Fourier coefficients of this Gaussian kernel, or this periodic Gaussian kernel, are just the Gaussian functions in, Fourier space. So these Fourier coefficients are e to the minus L squared, just like a Gaussian. Okay, let's look at that again, as I did with the top hat function. So here is my kernel, and remember the kernel, the argument to my kernel is the difference of the inputs. So this is x minus y, which is what I should have written here. Okay? Now let's say that I'm, this thing here, this red function, is a Gaussian kernel, but the Gaussian kernel just keeps repeating. So as I go past pi here, it goes up and then down and then up and then down. And it just keeps going over and over again, like Gaussian one after another. Okay? I'm approximating this Gaussian kernel now with a single cosine. Okay? Here are my Fourier coefficients. Not a good approximation. Let's add a second cosine with double the frequency. And I'm using here this weight. Okay? Remember, the weights are decaying like a Gaussian. It's already looking better. Let's add a third cosine. It's looking better still. And basically, if I add all the cosines, my approximation to my kernel using these Fourier basis functions is looking very good. Okay? So this is my kernel function, my Jacobi theta kernel, which is the exponentiated quadratic kernel for periodic domains. Here are the coefficients. Here are the eigenvalues of that, the eigenfunctions of the cosines, and I'm getting a very nice approximation to that kernel. Okay, so now I've got an expression, a Fourier expression for any function that I care about. I've got a Fourier expression for my kernel. Now I want to construct a reproducing kernel Hilbert space. Okay, so let's do that. So first of all, I need to remind you of something you would have learned in your class of Fourier transforms, which is like the standard dot product between functions with a Fourier representation. Okay, let's say that I've got f and g, and I've got this Fourier expansion for my f, sum over f hat, my Fourier coefficients, times these Fourier basis functions, and I do the same with g, sum of g times Fourier basis functions. Now remember, when I'm doing a dot product in a complex domain, I have to flip the sign of the imaginary part for the second argument of my dot product. Okay, when I do that, I can take the sum outside my dot product, so I've got the sum over f hat, g hat complex conjugate, times the dot product between these Fourier basis functions. Remember that the Fourier basis functions form an orthonormal basis. So this dot product is only 1 when L and M agree, and it's 0 when they don't. All right? So this dot product here, this double sum turns into a single sum, because all of the terms are 0 except for those terms where L and M agree. So this is just a dot product of f hat and g hat. Okay? This is the standard dot product for functions in the Fourier domain. Now I'm going to tell you the dot product for functions in the reproducing kernel Hilbert space that I'm going to construct. This dot product looks like this. It's a standard dot product where I've divided by the Fourier coefficients of my kernel. Okay? I haven't told you where I've got that from. I've just sort of specified that that is true. Okay? Does this work? We'll find out. Okay? So, but I've written these two down on this slide so that you can tell the difference. Like, this is the standard dot product you would use if you have a Fourier representation. This dot product here is the dot product that I'm getting when I'm constructing a reproducing kernel Hilbert space using the kernel with coefficients k. All right? So I just want you to sort of look at the difference between these two. Now this dot product here has a very particular property, which is it's a smoothness enforcing dot product. Unlike this case here. Okay? What does that mean? Let's look at the norm of f in this space. I've defined a dot product. Let's look at the norm of f in this space with this dot product. Okay? It's a dot product of f with itself, which is, you know, dot product of f, complex conjugate of f on k. So the modulus of f, the norm of f, so times squared times k. So, you know, when k, remember like the Fourier coefficients k, let's look at them now, right? These are decaying very fast for the exponentiated quadratic kernel, or for the Jacobi theta kernel in this case. If these k hats are decaying very fast, that means 1 divided by k hat must be growing very fast. If 1 divided by k hat is growing very fast, and I still want this sum to converge, then these f hat l's had better be decaying very fast. They better be decaying even faster than k hat l. Because if they don't, my sum is going to diverge. So this is why this is a smoothness enforcing dot product. Compare it with the dot product I would get here. This would be the sum of f hat l norm squared. Okay? Here I've got the sum of f hat l norm squared divided by k hat l. K hat l is decaying, 1 on k hat l is growing. That means my f hat l's have to decay much faster than they would otherwise. So basically, if I'm making my norm of f small, it means that I'm making my function really smooth. I'm forcing it to be smooth at a rate which is determined by these k hats. So these are well-behaved functions. All right? So here is a question. The top hat function that I gave earlier, is this in the RKHS? So who thinks that it is? Who thinks that it's not? Okay, the brave person who raised their hand is correct. So it's not in the RKHS. Let's see why, okay? For it to be in the RKHS, this norm has to be finite, right? My f of x can't be infinity. F of x equals infinity, that's not in my space of functions. Okay? So the sum of the f hat l squareds divided by k hat l has to be finite. Let's look at the k hat l for this case. K hat l decays exponentially as L squared, e to the minus L squared. That's a very fast decay. Okay, so I've got 1 on something that decays exponentially. That means it's growing exponentially. Now let's look at the f hat L. F hat L is decaying as 1 on L. That's a polynomial decay. So f hat L squared is decaying as 1 on L squared. So you've got a numerator decaying like a polynomial. You've got a denominator decaying like an exponential. That ratio, if you take the sum, that's not going to converge. That's going to blow up. So the top hat function is not smooth enough to be in the RKHS with this Jacobi theta kernel, with this kernel here. Okay? The reason it's not smooth enough is because these coefficients, these just don't decay fast enough. So this function is outside that space. So when I say it's smoothness enforcing, it's a pretty harsh smoothness enforcer. Are there any questions about that? Yep?
Just some thoughts, maybe you can directly into formulating a question, but as long as we have this translation invariant, I think we have for expansion.
Yep.
Then I understand that smaller diagonal is the linear function. But is this necessarily true for all kernels?
Yeah, so basically, like, you know, I'm going to order, I mean, so what I have done in a sense is like constructed a particular example where we know it's true because we've got the Fourier basis. To have that discussion for more general cases, like that will be more complicated. So, you know, this is why I'm using the Fourier example to illustrate this property. But yeah, in general, the property that the norm of the RKHS function enforces smoothness, that will always be true. A way to show it more generally, you can sort of show that the kernel is a green function of a differential operator, and that is a way of sort of understanding the notion of smoothness for general kernels. But I'm not going to talk about that now. For these purposes, I think for the Fourier case, we can construct it explicitly. We know exactly how it works. For more general cases, that's outside the scope of the lecture, but it's also true. Are there any other questions about this? Okay, so let's continue. Right, so here is my smoothness enforcing norm. And we know now that the top hat function is not smooth enough to be in this RKHS, which is kind of fun. This one I think I'll skip. Okay, so I've just said that this is my norm and this is my dot product. I can say that, but now I want to check the most crucial properties for reproducing kernel Hilbert spaces, namely the reproducing property. So, you know, remember the reproducing property. That's a property that says that the dot product of f and the features of x had better be f evaluated at x. And the dot product between features of x and features of y had better be the kernel between x and y. So I've specified a dot product here. Does that dot product satisfy those two properties? I don't know, let's find out. Okay, so let's first of all show this property here. Let's see if I can highlight it. This property here, right? This is the property that the dot product between f, coefficients f, and k of dot x, so features, k of dot z in this case, which is features of z, is equal to f of z. All right, I need to show this property. This is the reproducing property. If I can show this property, then that dot product that I've kind of arbitrarily defined is a valid dot product for reproducing kernel Hilbert space. Okay, so to show this dot product, I need to sort of think about what this k dot z is. Okay, so what I'm doing is I'm defining a function indexed or parameterized by z. Okay. So this is a function, you know, this x here is my sort of my dot, okay? And my z is a fixed parameter. And this is a function of x, like this is a Fourier representation of this function of f. Here are my Fourier coefficients, and here is my features, okay? So this is my g hat L, and this is my features. This g hat L is just the Fourier coefficients of my k times e to the square root of minus 1 L z. Okay, so this is just, you know, literally I've just taken some of my Fourier transform of k, and I've said this bit here is g hat L, my coefficients, and this bit here are my features. So my features are of x, and my coefficients contain in them the z. Is that clear, or are there questions about that? Okay, so this k dot z has these coefficients here, k hat L, e to the square root of minus 1 Lz. Let's substitute that in to to the definition of the dot product that I made earlier. Okay? Coefficients of f, well, these are f hat L. These are the Fourier coefficients of f. Coefficients of k dot z, well, these are k hat, e to the square root minus 1, L, z. Complex conjugate. So the minus sign here is, flipped to a plus. And then I've divided by k. Well, this is nice because the k's cancel. And now I've just got the Fourier transform of f, which is f of z. So what I've just shown is that in the dot product that I've just defined, the dot product between f and features of z is indeed f of z. So now you can see why I had this dividing by k thing here. That dividing by k was used to cancel the k here and to give me my f of z. Okay, so my dot product satisfies the reproducing property just like I wanted it to. Questions? Okay. In particular, if I take the k dot y and k dot z, I will recover k of y minus z. So this is something that you can do this evening on your own. It's a nice exercise, and I really encourage you to do it because you're going to understand better how this works. Okay. In particular, what you want to do is you want to define a second function with y, which is f hat L, which contains y and this thing here. And then if I take the dot product of this f with this g, which is to say I take the dot product of g hat L with f hat L, and then divide by kl, then one of the k's will cancel, and I'll get back exactly the Fourier transform of my kernel. So I have shown the second property here, this reproducing property, also holds. Now, in particular, this is the difference between the reproducing dot product and the L2 dot product. If I took the dot product between two kernels in L2, let's go back and see what would happen. Compare these two dot products, right? If I took the dot product between these kernels in L2, I would get an extra k hat here, right? Because I wouldn't have this k which would cancel. And so the dot product between two kernels in L2 is not, the kernel between the two arguments. It's something else. So this dot product here, this L2 dot product, isn't going to have the reproducing property. This dot product here is going to have the reproducing property. So this, dividing by k is necessary to ensure that the dot product between my features of y and my features of z is the kernel between y and z. Is that clear? Are there any questions about that? Okay. So what we've now defined is this smoothness enforcing norm. Okay. Let's go back to here. Yep. So what I'm going to now do is to tie in the construction that I've just made for the Fourier kernel space with the original presentation that I made for kernel feature spaces. Okay? Remember the original presentation I made for kernel feature spaces, I said that my f of x is a weighted sum of, fl times features of x. Now here, my features might be complex, so I put in the complex conjugate in case they are. Okay? So this is my dot product of f and features of x. Now, when I made my Fourier construction, I defined my dot product as f hat L, the Fourier coefficients of f, g hat L, complex conjugate, the Fourier coefficients of g, divided by the Fourier coefficients of k. All right? And in particular, remember the proof that we just did. The dot product between f and k dot z is f hat L, k hat L, e to the minus il z on k hat L. All right? This is what we just proved. Now, what does this line here have to do with this line here? So, be very careful of the difference between these two. These fl here and these f hat L here, these are not the same thing, right? The f hat here are the Fourier coefficients. The fl here are the coefficients that I've used when I've defined my feature space. They're not the same thing, but from these expressions, you can immediately see that they're very related, right? So if I just take my k, and I express it as the square of the square root of k, then I can immediately see that my features are square root of k times these eigenfunctions, which this is exactly what we've done earlier, and that the FL are the Fourier coefficients divided by the square root of the Fourier coefficients of k. So, compare this expression with this expression. If I substitute f hat L on square root of k with FL, and phi L with square root of k times e to the minus ILX, then this expression and this expression are exactly equal. So now we've basically tied in our Fourier construction with the earlier feature construction that we made, okay? My f hat L's are just the Fourier coefficients divided by square root of Fourier coefficients of k. My features are square root of k times eigenfunctions of my kernel, just as before. And then I've got this expression here. So my f is the sum of these features. So this is just very simple algebra, but I wanted to put it up so that you could sort of see how my earlier introduction of my feature spaces ties in with my Fourier construction. In particular, right, remember that I said that the norm of f was the sum of these FLs, right, the blue FLs. Well, the blue FLs are the Fourier coefficients divided by square root of k, so that indeed gives me the correct norm in my Fourier notation, which is the f hat L squareds divided by KL. So this was a certain amount of algebra, so are there questions about this algebra? Yep. So k hat L's are always real valued, and the reason for that is that my kernel is symmetric and positive definite. So k hat L is always going to be real valued. Yep, that's right. And even more than real valued, they're not going to be negative either. So because my function's positive definite. Yep. Yep, exactly right. Yep. Are there any other questions? Okay. So now I think, the really important thing to get from this lecture is that the norm of f in the RKHS is a smoothness enforcing norm. If I force that norm to be small, my function is going to be smooth. Okay? And this is the core property, like this whole sort of, 1.5 hour of talking is to lead up to this fact. And this is the fact that I'm going to be using in my second and third lecture. Like this is the core property of these feature spaces. The other core property is that I've got infinitely many features, and that's something that's necessary when I'm going to be doing what I'm going to be doing in the next 2 lectures. So, when I'm comparing probabilities, I need infinite feature dictionaries. That's the only way to do it rigorously. And I've constructed infinite feature dictionaries. So I sort of talked a little bit at the start that I would talk about ridge regression. So I think, kernel ridge regression is one of the very simplest, most elementary algorithms in kernel space. And what it's doing is it's just saying, predict y from f in squared norm. Okay, so yi from xi in squared norm using a function f. And my function f is in my reproducing kernel Hilbert space. So it's the dot product of these coefficients f times features of xi, okay, plus lambda times this norm of f. The lambda tells me how much I should care that my function is smooth. If my lambda is large, I really care that my function should be smooth. I'm really forcing it to be smooth as hard as I can. If my lambda is small, it's okay. My function can be wiggly. Okay? So remember the 3 plots that I did at the start of my talk. Here, I chose the following parameters, okay? Lambda is 0.1, sigma, the width of my exponentiated quadratic kernel, is 0.6. This gives me a nice fit. It's not too smooth, it's not too rough. Now what if I make lambda is 10, okay? When I say lambda is 10, I say I really care that my function is smooth. Even if, I care a lot less about this term, I care a lot more about this term. I'm really, really forcing my function to be smooth. I haven't changed the kernel width, right? My kernel width is exactly the same as before. I'm using exactly the same kernel, but I care more about smoothness. You get a very smooth function out. It's not a good fit, but it's very smooth, because I said that that's what I care about. What if I choose lambda very small, 1 by 10 to the minus 7? The function I get out is really wiggly. So basically, at this point, it's like, I don't care. My function could be as wiggly as I like. What really matters is that I get close to all my points. That's what this function looks like. So by adjusting this lambda, I can make my function more smooth or less smooth. And I do that by saying that this norm, this smoothness enforcing norm, is more or less important to me as I do that optimization. So here you can see in this very simple algorithm that this knob I can control of like emphasizing or de-emphasizing my smoothness enforcing norm is going to result in functions that are more wiggly or less wiggly. Yep. Okay. Let's see. So I've got a minute. What I want to do, I just want to show one quite cute little thing. The way that this is like a little bit of an aside, but it's an aside that those of you who are sort of functional analysts might find quite cute. I've defined reproducing kernel Hilbert spaces in terms of features and in terms of kernels. Here is another definition of a reproducing kernel Hilbert space. These are the Hilbert spaces for which the operator of evaluation is bounded. What does that mean? That means f of x, which is to say the f evaluated at x, is always upper bounded by a coefficient that depends on x and the norm of f. Okay? This is a definition, this is another way that you can begin to construct a reproducing kernel Hilbert space. One way is start with a positive definite kernel, define your features, construct your functions. The other is say, I have a Hilbert space and I want this property to be true. It turns out that this is an equivalent construction. Now this property is kind of cute because that means that, let's say that I've got two f's, an f and a g, and I take the absolute value of their difference, okay? This is evaluating f at x minus evaluating g at x. By this boundedness property, this is upper bounded by this lambda times the norm of the difference. That means that if these functions agree in norm, so if they agree in the RKHS norm, if the norm of this difference is 0, then they agree at every point. So think of regression. If my functions agree in norm, that means that they make the same prediction at every point. This is true for reproducing kernel Hilbert space functions. But it's not true for other Hilbert spaces that are not reproducing kernel Hilbert spaces. So remember the L2 dot product that we had before, okay? That's a Hilbert space. But this property doesn't hold in that Hilbert space. So the Hilbert spaces for which functions that agree in norm agree at every point, make the same prediction at every point, are the reproducing kernel Hilbert spaces. And these are the, this is, in a sense, these are the nice Hilbert spaces, right? So any Hilbert space that doesn't have that property is a little bit more troublesome because it's not even defined at every point, which makes it kind of hard to make predictions. So this is kind of cute. I had to mention that. Yep. So I think this is a good place to stop, I believe. Yeah. So I'm happy to take more questions. It's 1.5 hours, right?